Okay, I'm just going to test my clicker here. Yes, awesome. Okay, so first of all, if you're interested in reading all the content on the slides, please download them from the Event.yay page. The slides are built for a 40-minute version of this talk, so I'm not actually going to cover everything on the slides. Now, my name is Chris Travers. I am currently outgoing principal engineer at Delivery Hero. And this talk is more about something that's sort of been a hobby project of mine for a little bit, but I'm actually hoping to build a startup around. But on top of this, I want to spend some time and talk about some of the design trade-offs that go into the question of big data platforms generally, and the whole question about distributed data on Postgres. So we'll talk a little bit about why this project was built at a previous, or why the predecessor of this project was built at a previous place of work for me. Probably, yeah, we'll cover in a very brief way the general design of the earlier version as well as what we're doing now. I plan to spend most of the time looking at the current open source version and some basic discussions of trade-off lessons. So the rest of it will be heavily abbreviated. So before Bagger at Just, we used Elasticsearch. Elasticsearch worked great until we got a petabyte of data, and then it fell over. In fact, the joke was that it was an extremely expensive dev null because we could write to it, but we could never read from it. And it would fall apart for a bunch of reasons, including garbage collection, stop the world events, which would knock nodes out of the cluster, leading to rebalancing, which would lead to more garbage collection pressure. You wash, rinse, repeat, and everything falls apart, as well as the fact that some queries could literally crash nodes and then be repeated automatically until they crashed the whole cluster. So this became a big problem. Under the velocity that we were working with, we decided to build something else. So I'll let you just I've kind of gone through a very quick overview of this, but there were some very serious problems that we had. It was an absolute bear to work with, Elasticsearch was, and so some of these have gotten better, like if you used a newer garbage collector, maybe you can avoid the long stop the world events, but you still have the large queries that can raise Java heap exceptions, etc. So, so we had the idea of doing this minimalist design, fully schemaless. One problem we had with Elasticsearch is that since every time you see a new field, you have to index it, Elasticsearch is actually not very schemaless, while Postgres JSON B documents actually are very schemaless. And so we were able to have something much more schemaless simply by moving to Postgres. As strange as that sounds, the idea was we needed something linearly write scalable with very few limits, and we don't really need much read scalability, so that was more or less static. So the basic structure here is stuff comes in, goes into Kafka. Kafka partitions distribute the data. We read from certain partitions, write to Postgres, and in a random sharded way. This means basically you have to read from all nodes to get the information you're looking for. And because we had very large numbers of columns in our indexes, we actually had to have a patched Postgres. Although I think with recent versions, max index keys can be set with a simple compiler flag. So I think going forward, I think it could be done with a compiler flag rather than a formal patch. And then of course we have a C language routing trigger. So we wanted to open source this, but we had some problems. Too many assumptions. It was built really for a Just's workflow, and too many statically defined criteria that were Just specific. So we never really got around to open sourcing it. I kept trying to devote time to do that, and it never worked. So a few years later, I left to Just. Fast forward a few more years, and we met some people, or basically some of us got together, and we started writing a replacement. One thing I didn't mention is why we chose Postgres. Besides the schemaless bit, we also noticed that when we tested it versus things like Cassandra, we actually had the lowest write amplification of any of the systems we looked at. So Postgres had about 4 times write amplification, Cassandra had 8. And Scylla was much more like Cassandra than like Postgres. So there was a lot of analysis that had gone in that early stage. So we decided to build this. We basically decided to go with what had been the architecture of the early version as much as possible, including as many technology choices. This was basically built to have a baseline on which we can improve later, right? So some of the decisions we'll talk about in a few moments will look really strange, but they make sense if you're trying to establish a baseline of something you know works, and then you can test other things against them to make sure you actually have improvements. So these are some of the things that will look a little bit strange, like the fact that we have so much use of Perl, right? Perl is used in the ingest, basically the server management piece. It's used in the cluster topology management pieces, and it's used in the query pieces. And then, of course, C language triggers, because that's super performance critical. It has to be fast. And now we're in the process of selecting a front-end framework. So again, the idea here was to look into sort of what we knew and what we had previously used, although since we didn't have a front-end side before, that part has to be new, with the idea that then we can switch out pieces as we need to in order to improve the overall system. So here's the overall data flow, okay? You have your service network that's generating log files. Those log files will be generated in like JSON documents. Those get written to Kafka. Then you have these programs called Shuffle that basically read from Kafka and write to pairs of Postgres systems, although in the future we'll make it so they can write to a configurable number. And then on the other side, we have basically a front end that uses a REST API to query this proxy query, basically sends queries in HTTP format that'll generate SQL queries that'll run on all nodes and basically stream the results back. So fairly simple, fairly straightforward. And then the control overview is basically you have the Shuffle systems over there, the data nodes, the query proxy, et cetera. They all talk to metadata servers that basically store basically the desired cluster topology and desired node state. And then you have an infrastructure as code system that's there to basically provision and deprovision pieces. So what's actually not listed here is that the metadata servers changes are logically replicated to etcd, and then from etcd we have agents that basically make those changes in the shuffles or the data nodes or the query proxy. So if you want to take a data node down, you just write to the metadata server that the node is offline, and the agent will pick it up and take the node offline. So current status, we have the node control infrastructure done, the metadata server schema functions, et cetera, the replication to etcd, that's all done and tested. We have a Postgres config that allows the metadata stuff to be exported out. That's also done. What I'm currently working with, and I've been working on it for probably most of the time I've been working on this project, is a C language trigger, because it's complex and trying to make it work fast in a situation where we're heavily generalizing it poses some problems. But I expect that this will be done fairly soon, and then the rest of it will be pretty trivial. From there, we just have to write the query proxy and the front end. Both of those are relatively simple components compared to the compared to either the metadata server schema stuff or the C language trigger. And so I think we're moving relatively fast, aside from that one piece. So once we have this out, we want to choose a better language for the query proxy. Question is, what's that going to be? Golang is popular right now. There are some things I like about Golang. There are some other things I don't like about Golang. Some of the recent Java versions have a lot of nice features that might be useful. We're evaluating those. We will make some decisions. A second question is, would it be possible to have data nodes that are actually Citus clusters? We don't want to do full, we don't want to do just a simple Citus cluster because you sacrifice some write scalability with all the tuple routing that Citus will do for you. But if we had nodes that were, if we had basically data nodes that were Citus clusters, that might improve read scalability in a way which would still give us the ability to linearly add write capacity. So that's the second thing that we expect to look at. The question of read scalability, that's a tough one. We are looking at it. I mean, obviously, you can just add more copies of the data and distribute your reads, but maybe there's some better ways. Right now, we write twice. Is there a form of, like, you know, would streaming replication work instead? When we've tried this in the past, it has not worked, but we want to revisit that and see if things have gotten better. The issue is, WAL gets generated by many different backends, basically handing latches back and forth, but they get replayed by a single backend. And so if you have a very high throughput, you can overwhelm basically the replay logic, and you'll never get caught up. Finally, one of the things we really want to play around with is compiled block size. So by default, Postgres uses 8K blocks. You can compile it with up to 32K blocks. If we're using really big, if we're storing big JSON documents, instead of putting those in toast and external storage, would it make a lot more sense to put them in mainline storage in the main heap tables? My guess is probably yes, but that needs to be tested. And that actually gets to, like, you know, the question of, you know, how do you make money at a startup doing this? Well, if you're compiling Postgres with a non-standard block size, the number of users who are willing to do that for themselves, there's very, very few. So that's, you kind of get a foot in the door on that. And we have several other projects that we want to look at it in there. They also include things like, you know, foreign data wrappers for certain things, or custom table access methods for the kinds of data that we're working with. Couple points about trade-off lessons is it's real easy to have just write scalability or just read scalability, right? You can either break up your data just so you write it, you know, wherever, or you can have many copies of your data so you can read from wherever, right? Having, or you can split up your data so it's easy to read from many places, but then you have more work on the writing side, right? So trying to have both is actually really difficult, but this is one of the big lessons, is that if you have to do distributed data, if you only need read scalability or only need write scalability, then you're in much better shape than if you're trying to do both. Second really big point is benchmark everything. Again, you know, I think when we had previously started looking at the predecessor project, I don't think anybody really expected Postgres to be the winner. But when we started running all the benchmarks against Cassandra, against Scylla, against some of these other ones, Postgres actually had a really reasonable write amplification, and therefore that was one of the big reasons why we chose it. So benchmark everything, get to a good baseline, and be able to benchmark your changes. That's really important. And finally, there's the point of specialization versus generalization. Tools like Citus or Snowflake, et cetera, they're reasonably good general tools for certain kinds of solutions, right? But when you get into an area that's outside of their specialization, they break down in interesting ways. Similarly with this, if you were to try to use this as, say, a distributed data warehouse, it would break down in catastrophic ways. Usually what I found, and I think you'd see it if you look at this project versus something like Citus or Snowflake, is you're still going to find this situation where if you're in the core of a specialized tool, it will perform at least 10 times better than a generalized tool. But if you get outside that core, it will perform probably 10 times worse than a generalized tool. So that's the other major trade-off to keep in mind. So bonus learnings, know your requirements. Obviously, I think we've already talked about the fact that different problems require different architectures, which require different solutions. Linear scaling for writes is much easier than trying to do just writes and reads. Similarly, linear scaling of reads is much easier than trying to do reads and writes. So yeah. So there's the repository if anybody wants to get involved, take a look. And now I'm open to questions.
So first question, was it for production purposes or academic interest?
So you're talking. So the early version was for production purposes, and we needed something fast because Elasticsearch was necessary, but it was failing, and it was a problem. So some of us got together. We started saying, "Oh, this was cool. Let's build a new version of it." But now it's becoming a commercial interest for production.
Okay, and second question, like, did you consider using anything appropriate for work, like ClickHouse, like Druid, or some other columnar databases for massive data processing?
So for log management, columnar databases are absolutely the wrong solution. Now, if you're looking at ClickHouse, ClickHouse does have log tables that aren't columnar, right? They're just basically, when we looked at doing this at Adjust, we didn't, ClickHouse hadn't even been released yet, so it wasn't an option. We did play around with ClickHouse later in some other applications. I think one of the advantages that this system brings is that, like, okay, so how do I put that? ClickHouse is a great product, again, for certain kinds of solutions. But if you get out of some of those solutions, you get really, really pathological behaviors, right? So if you're writing to some sort of an LSM table infrequently but fast enough, you don't get the batching stuff, and you generate all these LSM merge stuff in the background, and you can kill the system with a surprising number of writes. Since we're not doing LSM stuff here, and we're not including any of that infrastructure, it doesn't pose a problem, and we still get all the atomicity rules that we get with Postgres. Well, ClickHouse's atomicity rules are quite different, right? So those would be the things I would say. I would say definitely people should evaluate both, should definitely evaluate ClickHouse, but we see some value in having sort of some of the more familiar atomicity rules and some of the other things here that we think some people might be finding.
If you don't mind, like 2 more questions.
Okay.
Basically, I will not agree with the fact that columnar is not appropriate for logs, but I will keep it to myself because it's an industry standard right now. As well, like, how do you handle compression for when you're storing objects in Postgres?
Okay, so I'm going to comment on the columnar piece first because I suspect we may be talking about slightly different things. Columnar is great when you're doing analytics on logs, right? But if your primary workload is grabbing the whole log message, all the fields, you're adding a lot of work for very, very, very little benefit. So yeah, I mean, there are use cases, right? Especially if you have older logs that you want to digest for metrics, definitely columnar is better there. For compression, What we're currently trying to do is we're looking at the question of if you have a larger, let's say, so one of the issues is if you try to use Postgres as compression, right, then you are just compressing one field at a time, and you don't get an ability to do any compression across different documents, right? Now, one solution to this, which is what we did at Adjust, was to basically run it on top of ZFS and have the file system compress things at the block level, so you can compress a larger number of documents together and get some benefits out of that. I think we were able to compress things several times what we could get with the built-in Postgres compression. One of the things we want to look at here is not only just ZFS, but also if there are perhaps new table types that would help, like Oriole, for example, where you have compressed blocks happening at the file system level in ways that might also be helpful. So.
Thank you. Basically, the point why I'm raising the columnar again, like it's not only helps to, like let's say if you would apply like Parquet for the work, it would help a lot with the data compression, with dictionary, whatever, ZSTD, yada yada. But it would also help you with various kind of like implicit indexes like Bloom filters or whatever to reduce the amount of search like data you would need to search for. So it would also help you with the row-based access as well.
The challenge there is if you have very large amounts of data and enough that you're finding that to cut costs you have to put it on spinning disk, then your disk access patterns are pathological when you're trying to grab the whole row. But again, yeah, well, let's have a longer conversation about this, because I agree with you that there are a lot of benefits to columnar in certain areas, and long run we actually do intend to build pipelines that'll write stuff to Parquet, but probably not just for straight log retrieval, but who knows?
Okay, thank you. Any more questions for Mr. Chris? Okay.
Thank you for your talk. I have a question. You were talking about the proxy for the queries that is not yet implemented. So can you tell something about the workloads this proxy should work with? So it should be really distributed queries like distributed joins, or it should be something like sharding.
Yeah.
You were talking that it depends on whether you choose write or read.
So given that this is just aimed at log management, right, we typically are not going to have joins. And so it's going to be purely sharding and purely partitioning. So what the query proxy needs to do is to generate appropriate SQL queries and then basically run it on all of the data nodes, and then basically stream the results back so that you don't have a large amount of stuff piling up in memory that needs to be processed. Now, in terms of the workloads, the typical thing would be like, show me all log entries between this time and this time where the following filters are true. And so in this case, they would probably be simple tables. Our current approach, because that's what we did last time, was not to put the partitioning in Postgres, but to do the partitioning on the application side. So the application would then have to figure out what tables to query and generate queries for all of those tables and send them.
And do I understand correctly that the application somewhere keeps some metadata with distribution columns for sharding, and according to the where filter or where condition, it finds out on which shards to go?
Okay, so that information is then actually stored. Okay, so you have some general metadata that says these are the various servers that are active for a generation that starts at this point and ends at this point, right? And then within each of those servers, or you'll have two schemas, one for, or potentially eventually multiple schemas for each set that's written by one of the shuffles. These will then have, within the schemas, then you'll have time-bounded columns, time-bounded tables that will be partitioned according to some user-specified So the user-specified criteria for partitioning is in the metadata systems, but the exact timepieces, the exact time-bounded tables, we have to check the system catalogs in the data nodes.
Okay, thanks.
Thank you. Any more questions for Mr. Chris? Right. If not, thank you so much for sharing about Bagger. Yeah, if you need to keep in touch, please. Yeah.